Today we're going to be talking about maxima, minima, and the extreme value theorem. So the absolute maximum and the minimum of a given function is the point on the entire graph with the highest y value. There can only be one absolute maximum within that range, and the absolute minimum of a given function is the point on the entire graph with the lowest y value. Again, only one absolute minimum. So as we look through these, we're going to talk about local and we're going to talk about absolute. Local talks about those high peaks and those low peak valleys, while the absolute is talking about the absolute high and the lowest of lows. So as we look at example 1, we're being asked for each problem to find all points of the absolute minimum and maxima and then give on the closed interval. So making sure that we're keeping it to that graph. So as we take a look at these, for instance, on example 1a, if I'm looking for the absolute max, I'm trying to figure out within that graph what is those values. And we are being given on the range on this of our values we're looking within. We're looking from -3 to -1. So just in that little section, we're trying to see what is the highest point. And endpoints can be included when we're talking about those absolute values. So if I take a look here within that little range that we're looking at, that little window, we can see that the highest point is taking place at -1.7, which is right on that boundary, but it's fine because it's included. So make sure that we're paying attention to that as you're determining if it's included as part of that max or if it would be the point just before that. For my absolute minimum, again, looking at that graph, and trying to see within that window where is that lowest value. And I can see again it's happening on that boundary. So thankfully that boundary is included. So it's taking place at -3.3. I want you guys to go ahead and try to do the same thing for B and C, being very cautious of if those values are being included or not on the endpoints. So for example 1b, our absolute max actually doesn't exist. We don't have an absolute max if we're looking from 0 to 3. There's no finite point since it's not given that we are being included on this side. So we don't have like a finite point where it can be. My absolute minimum is taking place at 2.7. Again, it's like an obvious dip, it's an obvious valley. If we had included 0, then we could have called that our absolute max, but because it is not included, we don't have that high peak there to include, which is why we state that there's no absolute. For C, you should have found that your absolute max is taking place at 0.2. while your absolute minimum is taking place at 5. And then for a question like this, since I want to know that exact moment that it's reaching that peak, I plugged in 5 to my original equation, which gave me 8/29. And you could also write that as a decimal, but make sure that when you write it as a decimal, you're rounding to 3 decimal places, just as you would expect to see on College Board. So with this, we talk about the extreme value theorem. Remember, theorems are super important in calculus. There's only about 5 of them, and typically they show up on your free response questions on the AP test. So the extreme value theorem states that a function that is continuous on a closed interval has an absolute maximum or a absolute minimum on that interval. So as long as it's continuous, where everything is included on there, you don't have any holes or discontinuities, then the extreme value theorem applies. With that, we also bring up the local. And again, I mentioned that the local is like those highs and those lows without having to be the highest of highs or the lowest of lows. So in example 2, we're taking a look at a graph with several different points. The points we're specifically looking at are labeled along our x-axis. And we're trying to determine or identify the points at which the local and the absolute extremes are happening. So if I took a look at example 2a, the first thing that I would look for is my local maxes. So I'm looking for any sort of peak that's happening here. When I take a look here, I see that I have a peak, and those values are happening at P and R. I wouldn't include B as being a local max because we don't know what's happening on that other side. If I had known that it was continuing in a downward trend on the right side of B, then I would include that. But since I don't know that, I have no idea what that function is, we don't have enough information to include B as a local max. However, if I take a look at an absolute max, I want the highest Y value possible. So thankfully, this is a closed circle on B, which means that B is going to be our absolute maximum. We're going to do the same thing with our minimas. So I have my local min, which are all my little valleys. I have a little valley at Q. I have a little valley at S. So those would be my local minimas. Again, on A, we don't know what that trend is doing. A could be continuing down into the lower quadrant there. So since we can't predict what's happening on the left side of A, we can't include it as a local anything. Local are your valleys, your peaks, not typically those endpoints unless you know what's happening on the other side. This does make my absolute minima point A, as that point is included, and within the graph that is the lowest Y value possible. I want you guys to try example 2B and example 2C. I will post the answers to 2B and 2C in the class notebook for you guys, but I want to be sure that you're practicing them so that if you have questions, I can answer them for you. As we talk through the local extreme points, if a function has a local point at any point C and the derivative exists, then you can actually find those local values by taking your derivative and setting it equal to 0. When we do that, we refer to those as your critical points. So if a question asks me to find my critical points, what we're going to do is we're going to take that derivative of whatever function that they've provided, and we're going to set it equal to 0 to see where those critical points are happening. So those critical points are showing me where that slope is changing from positive to negative, which is why we can determine that those are critical points that would tell us if there's some sort of peak or valley there. So again, I'm only going to work through one example with you guys, and then I'm going to have you guys check the class notebook to find and check your answers for the other problems. So if I took a look at the first example, the first thing I'm going to do is I'm going to take the derivative of my function. Thankfully, these are nice just power rule ones happening here. So if I take the derivative of the first term, I'm going to have 3 over 8x squared minus 1/2. And then I don't know about you guys, but I'm not a super big fan of fractions. So if I were taking this problem myself, I would multiply this entire thing by 8 so that I could work with whole numbers as I try to solve this for those critical points. So if I multiplied this by 8, I would get 3x squared minus 4 is equal to 0. I haven't changed the problem. I've kind of made the numbers larger, so then that way it is easier for me to solve. And as you can see, we end up with something that is much easier to solve than what we started with. So I'm going to go ahead and add my 4 to both sides. And then I would divide both sides by 3. So I'm using the square root method of solving to find where these critical points may exist. And then when I square root both sides, I know that I end up with square root of 4 over 3 as a positive, which simplifies to be 2 over root 3. And I know that I end up with a negative solution as well. So I would find all of these critical points first, and then make sure that things exist within your domain. So in this domain, they asked for -1 to 3. So this second one is actually not in my domain. So my only critical point is happening here, where x is equal to 2 over root 3. So just the positive of that solution. We could always rationalize that, but remember, you don't get points for simplifying on the AP test, so it's always safest just to leave it unsimplified like this so that you have less room for errors or less room for mistakes. Okay, I want you guys to try B, C, and D. Remember on C that you do need to use the product rule. And then you'll need to use a little bit of your unit circle knowledge in order to find the critical points. And then on D, you're going to need to use quotient rule. And I'll post those answers in the class notebook so that you guys can check on those as well. But I do want you to try them and practice them. And then the last concept that we have to talk about is how to determine from those critical points which ones are those absolute extreme values on that interval. So as we work through these, the first thing you're going to do is you're going to locate those critical points. When we locate those critical points, that's when you're taking that derivative of your value and you're setting it equal to 0. So I take the derivative of my function, set it equal to 0 to find those critical points. Once you find those critical points, you're going to plug your critical points in to your original equation to find that value. You're also going to be sure that you test your endpoints because that seems to be something that always gets forgotten. But endpoints can also be candidates. We saw that. We saw that we didn't necessarily include our endpoints as part of our locals, but typically our endpoints ended up being our absolutes because we don't know what's beyond them, but we know that it is the highest y or the lowest y. And then if the interval is an open interval, then the absolute value extremes occur at interior points. So they have to happen with inside. Again, I'll walk you through one of these and then I'm gonna have you guys try the other ones and I'll have you check your answers in the class notebook. So in example 4a, the first thing that I would do is find my critical points. So we're gonna take the derivative of this function, which is 4x cubed minus 6x squared, and I'm going to set that derivative equal to 0. If I were solving a question like this, I would pull out a 2x squared, which would leave a 2x minus 3 behind. Again, I haven't changed it. I just made it look a little different so that I can set 2x squared equal to 0, and I can set 2x minus 3 equal to 0. When I solve 2x squared is equal to 0, I get that one of my solutions is 0. When I solve the second one, I get that my second solution is taking place at positive 3 over 2. So these are my candidates for my critical points. So I have critical point at 0, and I have a critical point at 3 over 2. Step 2 is to plug those functions or those values into that original function. So a question like this, a calculator might be handy, so then that way you can go ahead and use your y equals, where we would plug this function into y equals, and then we would do the alpha trace so that I could plug in those values without having to continually type the same function over and over and over again. So I plug in these values, and when I plug in these values, I plug in 0 because that was the first critical point I found, and when I plug in 0 to the original equation, I got 0. I then plugged in 3 over 2 into that original equation, that original function, and I got negative 1.687. And I know it's 0.6875, so it's kind of on you if you would round to 0.688 or 0.687. So I tested both critical points, and then we test our endpoints. So I plug in negative 2, and I plug in my positive 2. When I plugged in negative 2, I got 32. And when I plugged in 2, I got 0. So that would be our step 2. And then our step 3 would be choosing the largest and the smallest to determine where is those absolutes taking place. So since negative 1.687 was our lowest value, we would state that this would be our absolute minimum. And then our highest value was 32, so this is going to be my absolute maximum. So not a ton of work. On C, I would definitely use your second trace when you go to take that derivative. I'll go ahead and go through C with you guys as well, and then B you'll try on your own. So B, you'll have to check your answer in the class notebook once you've attempted it. So on C, just because it is more difficult, if I were to take the derivative of C, the first thing I need to acknowledge is that I'm using product rule. So I have the first times the derivative of the second. The derivative of sine x is cosine x. Plus the second times the derivative of the first. So the second is sine x. And the derivative of 2 to the power of x is 2 to the power of x ln x. And this entire thing I'm going to set equal to 0. I do see that they all have a 2 to the power of x in it. So personally, if I were solving this problem, I would take that out. So it looks a little less intimidating. So I would set 2 to the power of x is equal to 0. And I would do cosine x plus sine x ln x is equal to 0. Now, I could try to convert this 2 to the power of 0 is equal to, ln 2 of 0 is equal to x, except we know that ln's can't be 0. So this is actually going to provide me with no solution. So I'm glad I took it out to try to make my life easier. If I were doing this problem on my own, I would plug this entire thing into y equals, and then I would plug this second function in, this y equals 0, as a second function so that I could use the second trace option and see where they intersect. So I'm using that intersect option in my graphing calculator to help me figure out where those are intersecting each other so that it's not a guessing game. When I plugged this into my calculator, there were only a couple of options in which we actually met at 0. One of those options was at negative 0.965. Another option was at 2.177. And then my third option was 5.319. And then you'd want to be sure that you also test your critical point or your starting points, which were negative 2 and positive 6. So when I plugged these into the calculator, or into my function using that calculator, for the first one, so my f of negative 0.965, I got negative 0.421. When I plugged in 2.177 into my calculator, in that original function, I got 3.716. When I plugged 5.319 into my calculator, 5.319, I got negative 32.797. And then I'm testing those endpoints, so I'm plugging those back in. And then I am checking those to see which ones are going to be my absolute max and which ones are going to be my absolute min. Okay, so all of this will be in the class notebook for you guys. Complete the problems that I did not do for you guys, and then you can check your answers in the class notebook as well. For this question, when I plugged them in, I got that my absolute maximum is happening at 2.177. And then the one that happens at negative 32, so when your x is 5.319, that's going to be my absolute minimum. So finish the examples that I haven't done for you, check your answers in the class notebook, and then I would suggest doing your independent practice for tonight. I have also posted your optional multiple choice for your upcoming assessment. Don't forget that assessment, part of it will be going in as your final, and the other portion will be going in for the unit. So I would strongly suggest looking at that optional multiple choice to ensure that you are as prepared as possible for that exam. If you guys have any questions while I'm out, you can try to message me. Otherwise, you can email me and we can set up a time to talk about these notes the week after Thanksgiving.